Hello and welcome everyone. Hello, hello. Come one, come all, come gather around. Let the attendees come in and file in. Luckily got a pretty sweet quick one. Just a couple of, so they say, housekeeping. Since I was unable to get a panelist, if you have quick questions, you can throw them my way. I'll most likely answer them at the end of the presentation. But you can also put in your input in the chat box. This is, this will be allowed to be a pretty interactive webinar. So we'll just wait for everyone to get in. I'll kind of go through the introductions as everyone comes in. I am John Nikoloff, Applications Engineer with GoEngineer. Hello, welcome everyone. And I'm sure everyone is getting ready to get back to getting out there and getting to see customers and everything. This will be a little parallel to that. This will be Soooo, SOLIDWORKS, GoEngineer's tips and tricks for contacts, contact sets. We'll basically go over fixtures a little bit as well. I kind of snuck it in there, but you can't get away from fixtures without within contact sets, right? Cool, come on in. Oh, hey, Jordan. Hello there. Great to see students coming in. Very nice, very nice. If you guys just want to say hey, throw it in chat too. We're all pretty friendly. All good stuff. Yeah, we also do teaching classes, and this is kind of a cool way so we don't always cover everything in the classes, so we can get to do these webinars to show really the nitty-gritty, so to speak. Cool. Alrighty then, we will get started. Since this is a pretty quick one, whoever else is going to come in, we'll just welcome on in. So cool. Contacts, so 2020, contactless, so 2020, right? We're all going to get ready and into it. There we go. So where have we seen contact sets before? If some of you have taken the online training or any training course with SOLIDWORKS, you've probably recognized this cardan joint. And here I have just put this picture up because it's really a great way to just show how the surfaces that we can contact with each other in a certain assembly. We can specify no penetration, virtual wall. We have a lot of options to make sure that our surfaces don't interfere with itself. Or if that's something we would like to do in our study, we can emulate that, but it's pretty nuanced if you want to do that. We've also are able to take large assemblies and simplify them into smaller sub-assemblies and apply all of our force loads and fixtures and contacts and all of our fun stuff that way. Nice. Varun, welcome. Thank you very much. So yeah, we've seen these around, we've seen these a bit, but what I wanted to talk about today kind of brings in a lot of other concepts. I wanted to compare what really no penetration contacts mean, bonded contacts, allow penetrated contacts, lines versus planes, how do we fix our models, right? Because if we have faces touching each other and we're going to have a lot of forces loaded onto that. For example, in the purple here, this is where I have my force load, and in the green I have a lot of fixtures. We're going to need to make sure that we keep those ideas very, very similar to each other, because contact sets are contacting pieces and faces in your model, whereas our fixtures is our way to tell SOLIDWORKS, hey, hold this at this particular spot, whether it's a plane, a line, or a vertex. Or if we wanted to create a virtual wall, which is basically creating a plane. So if you're fixing, as we did in the cardan joint, the entire assembly was attached to a wall that we just created within SOLIDWORKS, just a basic plane, and we'll be able to compare how that actually works within comparing to a fixture of just a fixed geometry face versus specifying how rigid we make this wall or how flexible we make this wall, right? Because we may not always be doing studies with solid surfaces. They could be surfaces that have give, or maybe it's whatever the case may be. It may not be that solid as, say, metal. It could be more soft as like wood, or who knows, maybe a piece of mouse paper, right? Cool. So contacts per design. A little bit of background. Contact sets allow us to tell SOLIDWORKS what surfaces we want to touch, which ones we are okay with interfering with each other, and which ones are stuck together. And by default, we'll usually start with a bonded contact, right? And then we can specify no penetration contacts for certain faces and for certain objects that are moving within each other. Sorry about that, guys. I hope if the webcam is bothering some, I can always just go into non-camera mode just in case, you guys. But if it is not that big of a deal, don't worry about it. But if it is, just throw it in chat and I can just save the bandwidth a little bit, right? Cool, cool, cool. Sweet. See a couple more guys filing in. Welcome, ladies and gentlemen. Just getting into contact sets, literally. So cool. First, I wanted to note no penetrating contacts are great because that's the way we tell our models to stay rigid, to not go within the borders of each other. And it doesn't stick them together. They're free to move, which if you need to define a friction constant, you can do that too. Bonded contact just keeps everything together. If you have different parts that make up a box and you're applying a load to it, if we squish it down, it'll move those faces if the surfaces aren't bonded together. So that's where that comes into handy. Allow penetration contacts, kind of like a caveat, where if you know that your model isn't going to interfere with other surfaces in the model, then it's allowed to, quite literally allowed penetration, but you're essentially telling SOLIDWORKS, hey, this behavior is something that we can predict or something that we know won't happen, so you can run the analysis allowing these surfaces to move within each other. But you have to keep in mind that this could lead to inaccurate results because you are losing a lot of the stiffness and a lot of the constraints that you're putting into your model when you just define a contact set, which I will show later. Shrink fit is actually very much of a nuanced thing. However, if you have surfaces that are spherically, trying to come together and they're not the same size, then you'd want to use a shrink fit contact set. Now, unfortunately for this example, I and my colleague Eric Vega, we worked on this model a little bit, and the parts do not overlap, so everything fits nicely. So we won't be displaying shrink fit, but say you get a design that's coming from another company or someone else in your team, and for whatever reason, even if it got translated weird from one computer to the next, something is a little off, or if someone just had a slight miscalculation, happens all the time, I included, shrink fit's a great way to trim those surfaces and tell them, hey, this is supposed to fit together. Don't worry too much about these faces that are technically interfering with itself. Likewise, if you run it with allow penetration, you may force that penetration through the other surface so far that you'll get very inaccurate results, and you'll be breaking physics within SOLIDWORKS, which is fun, but not so helpful for design work, right? And virtual walls, I kind of spoke about that earlier. That's another way we can tell SOLIDWORKS to not pass through a certain plane of area, and we have to specify how rigid this wall is. We have to specify the constants for this wall if we're going to tell it to hold this model instead of using a fixed geometry fixture, because that'll basically hold our degrees of freedom, which I'm gonna segue into now. So component contacts, what are the different types? I kind of spoke about degrees of freedom, where we have nodes and elements. These elements can also build up, these nodes and elements build up surfaces, and depending on our model, we're going to need to specify node-to-node contact, node-to-surface contact, or surface-to-surface contact. And this is really important for us to remember because we have to keep in mind how many degrees of freedom are we locking in with a certain parameter that we're trying to input. Are we trying to fix something at a certain point, not allow it to move? Do we want it to continue to rotate but hold it at a certain point? Or do we want to hold its rotation in place and just get its translational degrees of freedom so that we can understand the displacements in just x, y, z coordinates, positive or negative? Or do we want to get its axial displacements, both in radial pi or negative pi? Or if you continue, just keep going pi, right? Great. So cool. But if we don't know where to start, SOLIDWORKS comes in handy because by default, we just get a bonded contact at the very beginning of our setup. And this can be specified to be no penetration or with a bonded contact. These are all great things. But one great thing I want to take home, I want you guys to take home, is that by specifying local contacts, we're able to better define how our model is being constrained, and we're not going to add unnecessary rigidity to the model because the bonded contact holds everything together, right? But we're having to, at the same time, we may have to fight with SOLIDWORKS if we keep that bonded contact because it's holding things in place in free space, right? Wherever we have it in our SOLIDWORKS window, it's going to hold it there. And whenever we run our analyses, it's going to remember that bonded contact. So in this example, I'll show when I run an analysis with a bonded contact, and then we'll move the bonded contact and specify all the individual fixtures and contact sets so that we can understand if bonded contact is really the most accurate thing for our model. It's cool. Gonna now, minor spoilers. Boom. So wait. So great. Here is our model. Here I have also just kind of suppressed these guys. I'll go back and show you guys everything from scratch, of course. So I have these two hinge pieces fixed with a pin in the middle. Some of you guys who may have taken some of the classes may recognize that you could also replace that pin with a hinge, and you may have noticed that the hinge is down here as well. Clever, very good on you. We will get to that too. So here, basic case study. We have a part that has a revolving piece around it, and it's being held together by the pin right here. I have my contact sets right here. The first one is for the pin, and it is actually taking this entire face of the pin and telling it to not penetrate within these given inside surfaces of these parts right here. And I have this for the bottom piece right here and for the top piece. And that is what pin 2 is specifying. Excuse me. Contact set 7 right here. If we open up this guy, this is basically giving us a constraint that is not going to allow these surfaces to pass within these this part on the left and the part on the right. Makes it so that I don't select the faces that I don't want to select, and it makes it so that these surfaces don't pass through each other. So it keeps the model pretty close to what we would expect if we were to empirically test these. The next, I specified a rotation contact set. Let me open this up to show you. Cool. So I chose this interface, and if you guys can see it in purple, the interface on this bottom kind of nut is just holding the pin in place, and I don't want that to pass through the bottom surface of that rotating hinge. And the last one that I specified up here is doing the same thing for the top pin. So I'll just unsuppress that just to show you guys. So that's basically keeping the interface of this nut highlighted in purple. Get you a little bit better view for that. Sweet, right in there. And the blue is coinciding with the top face of our rotating part. Just check in questions and chat. Oh, you can see it now. Okay, great. Yeah, sorry about that, guys. Oh, you guys only see the... Oh, okay. Oh, not seeing the SolidWorks screen. Sorry about that, guys. Oh, it is? Okay, great. Sorry about that, guys. Yeah, I may turn off my webcam to save a little bit of bandwidth, if that's okay with you guys. I'll give it a second, though, just in case things need to catch up. All right, I'll just cut this. I'll cut the feed for... Okay, it's good now? Okay, cool, cool. Bring it back. Okay, so... just really quickly go through the contact sets. Sorry about that, guys. So the inner pin right here is making sure that I can't pass through the top hinge part. The second one's for the bottom. And these are making sure that the surfaces don't cut within itself or the other part. And these are my caps, basically. But say, you know, we're not really wanting to see all that. We just want to test the global bonded contact. And as promised, yes, we'll show this. And by default, component contacts in global contact bonded compatible mesh, this will be imported automatically for you whenever you open a static study in SolidWorks with an assembly part. And to write it home, let's start it from scratch. Awesome. Really appreciate everyone giving in the feedback as well. Seriously, thank you. So we'll call this web demo. Awesome. And there it is, lo and behold, our global contact. This is basically going to hold everything together without us having to specify what's in between the surfaces. So I'll apply my first fixture, the fixed geometry, grading audio, Fixed geometry is going to be the first one that we're really going to touch on. And that's just going to be on this face. Swing it around. Make sure just the face is selected. I'll apply a load of just a force pushing down on this face. And I'm going to select the direction to be along direction 2, which I believe should be in the Z direction. I think I gave it, what, 400, 200 newtons? And we're going to need to display this. Whenever we specify a force, we have to give it a reference if we're going to specify its direction. I'm going to give it this line so that we're basically telling it to go down this face, but I'm also to reverse that direction. There we go. I think I specified it as 400 newtons before. So we'll do the same. It's cool. And that's as simple as it is for setting up a fixture and a force. If you guys already know that, then we'll just quickly move on. I'm just going to run the study, let the mesh do its thing with a very coarse mesh. If you have any predictions of what's going to happen, feel free to throw them into chat or the questions area. Kind of keep a fun guessing game. So all right, our part didn't explode. That's good. The bonded contact holds everything together, right? However, let's just edit the von Mises stress plot, because I want to see this in megapascals. Cool, so 30 megapascals. Pretty high stress concentration. Of course, we need to run probably a better mesh to run, to avoid hotspot diagnostics and all the singularities that come with that, and really odd meshes. So let's test how good this global contact is now. I'm going to right click. Well, actually, I'm going to hide this first so we don't look too much about the spectrum of forces. Here we have our contact set. Ooh, clicked the wrong button. Contact sets right here. Open this guy first. And I also really like to show the keep visible pin. This is going to make it so we don't have to open and close the window all the time. It's very nice. And, before I'll go back to global contacts, because we can also specify it to be no penetration contact. So we can test that after we do the individual faces. So let's start from the top down. So automatically when we look at this, intuitively, we're probably going to figure out, okay, yeah, you push down on this. If we don't specify anything, we're going to pop that pin out of the hinge, and the two hinges are just going to break. So let's go in here, right click to select other, so we can select the opposite side. Note, if you do choose the inner face, it will go into the pin. Let's just go outside of it really quick. And there we go, the interface of that first little nut. And we are going to make sure that doesn't pass through this face. And I'm going to say no penetration contact. And remember when I said if you have frictional constants here, you can apply them, especially if it's with respect to your model, to your data set. Since I'm a physics nerd and we do all of our experiments without friction, we're just going to keep it simple and not include friction. You can automatically find the contact sets. That's also something that you can do from a top-down kind of thing, and I'll show that once we're done here, because I'd like to get to the actual nitty-gritty first. The next, we're going to need to make sure this pin doesn't pass through our faces on the top part. I believe we can also give this a shot and see how well it works if we just try to tell it all in one command to not pass through any of those. And I selected the same face of the pin. Yeah, that's that face of the mirror. Great. So I have the inner face of the top part. Let's go down here. Go and select the next. And you can also note the highlighted line in orange. Kind of is our guide. Sweet. Select the next one. Great. Making sure that our pink target is highlighted after we click it. Sweet. So here we have now told the pin not to move beyond the faces within these hinge parts, and that is denoted in the pink. Likewise, with respect to the left pane here. So great, we'll consider that a contact set. And next we can go in to the next cap. Make sure this all stays together. Great. So now that we have the pin constrained, we can unselect the pin, click OK, and let's remove this global contact. Everything is specified to no penetration, and let's see how we do. That was not supposed to happen. Sorry about that. Any questions so far? How's everyone doing? Sweet. Ooh. Wow. Thank you, SolidWorks. Alrighty then. Able to get another reading. Looks like we got 57 megapascals, but it's within this guy right here. So alright, we are definitely seeing a difference between just keeping a bonded contact and our individual contact sets. That's really great to know. And for consistency, let's suppress these guys and change the bonded contact to a no penetration contact and just compare the results. No penetration. Yes. And we'll unsuppress it. And run it again. Just keep in mind we had less than 60 before, now we hit close to 60. Oh, great question. Will the recording be sent out to attendees? I will post this on the YouTube channel, and you're thinking ahead because I will show the YouTube link at the end of the video. But since everyone's attendee list, if it's really important to you guys, I can totally send it out to you guys and make sure you have the link. Otherwise, you can check out our YouTube channel on GoEngineer YouTube, and this should be posted within a couple days, within a week, give or take. Yeah. We may also run a little bit over 30 minutes because I've been talking a lot. So I'm going to try to get through as many different comparisons of the fixture sets and the component contacts and see how the fixtures really affect it and everything. I can also, I'll also, whatever I don't cover here today, I'll also be releasing as content because contact sets are pretty fundamental, I have to say, for running simulations, right? Because we're going to see that if you run a global contact with no penetration versus bonded contact, huge differences. And seeing how this is taking forever, we may have done something to upset SolidWorks, right? What's the best way to handle contact sets for interfering clearance surfaces that will be in contact once assembled? Oh yeah, so in our contact sets, you can specify gap clearance. So you can tell SolidWorks how much space is in between. You can tell them how much space is in between your two parts. At the same time, that's where you can go into our advanced settings and give it a node to surface contact, just so that you're telling SolidWorks, hey, at a certain point, it'll eventually make contact with the face. An example is two plastic parts that have a gap between them until the screw tightens it. Okay. What you can do instead of giving it a gap clearance is you can just emulate the parts being held together and put in all of your, you can essentially say that it's bonded and specify how much force is being applied to that area as well, and that should also give you a good way to model it without having to necessarily put in a pin. So I'll show that next too. And it finished, and we didn't upset it too much. Our parts are still in our design space. That's great. Nothing flew out into empty space. And it looks like we did get a different answer than if we had bonded contacts. So specifying all the contacts, contacting faces and saying, hey, don't pass through itself. We did not actually get the same thing as a bonded contact. So which one's most accurate, you ask? Well, the independent contact sets, right? Because the global contact's just going to hold everything together. It's not going to be as specific as our individual contact sets, say for right here. Cool. And I was going to do this from scratch, but seeing as we're a little short on time, I'm just going to show you guys the Hinge example. And I have other couple extra... Oh, okay, this is a global. Okay. So I'm just going to run this really quick for you guys and answer the next question. But just so you can see that you don't have to have the pin in there, you can just hold it together and use a hinge fixture and contact the faces. Boom. Which version am I running? I'm actually running SP1. I should be running SP5. Bonded shrink fit wall. If you have no penetration contact, then you may have to go into connections and go into component contacts, and then this should give you the options to where you can actually select the entire part instead of just faces, which is totally fine, depending on how you're restraining things. Also, I did want to show off this reference geometry fixture because, like I said, you can hold things at a certain vertex. Uh-oh. That's not it. Sorry. This is an axes reference geometry fixture. So if you have a no pin to really model, but you want to throw an axis in the middle of your hinge part, you can also do that and tell it not to rotate about that. So you can keep it just translationally in your, I think this is Z direction for me. Just so I show you guys, hide this guy really quick. I want to change this so that you don't have to have an axis. You can have it on a vertex instead. So say you want to hold it on a line, but it's not giving me the option to give it a vertex. Let me go to another example to where I can show you guys. I have a question about meshing with contact simulations. Split lines, boundary conditions, contact surfaces to ensure that there are all nodes along the boundary. Is there a more efficient way to build? Oh, okay. So you can run your mesh as incompatible, so you can have them so they're not essentially overlapping. It's nodes together. They're essentially going to break it, but that is in a mesh option. So I guess I can show that really quick, but I want to show the reference geometry fixture right here first. Yeah, so here we can also specify a vertex with this face. So we're essentially saying this one can't pass much farther. Going to basically say 0 translation. Another way of fixing it in place. Great. I'll just run this guy, take care of the last question. And I do apologize, guys. We will definitely be able to cover more of this content in future videos, and in a week or so, I'll have this uploaded to our YouTube channel. Contact is the same as the old no penetration contact. Okay, that's great. Yeah, I think yeah. The later versions kind of included it, right? Cool. As this guy runs, I'll show you guys our YouTube channel, or show us the links after we recap. So we showed that there's a difference between bonded no penetration contacts, and we didn't have to apply our shrink fit fixtures here because there's no overlapping parts. And allow penetration, I can show that really quickly, but if we wanted to, since we're not working with absurdly high von Mises stresses of 1,000 megapascals, we didn't have to worry about allow penetration. And if we turned on virtual walls from the fixture, it does differ. And I also just want to show that since we still got people attendees, and I apologize if we're running over time. Just wanted to at least cover everything so those who have to leave can. But yeah, so we have our newsletter. You can go to our website and sign up for that. We also have our training and our YouTube channel, just YouTube-GoEngineer. So that technically concludes everything, but for everyone who is still here, I do want to show off those last little parts and show off some of our further capabilities. So sweet. This reference geometry, I just have it, I just have it unshown. But cool. It was able to hold this guy in place. And keep our model set. Let me go to the configuration for my virtual wall. I think it's a nice static 4. It's in the bad reference. Awesome. All right, let me specify some of the, make sure these guys are all set. Remove this. Unsuppress these guys. Cool. And I'm going to remove this fixed geometry and essentially just created a virtual wall to hold it in place now instead of the fixture constraint, which we'll be able to see how the degrees of freedom change. Because right now we've only seen fixtures hold on to this one face. Now we'll have a virtual wall hold it. And I gave it very basic inputs for its rigidity. Gave it 400 newtons per meter squared. So tried to at least give it some type of relative give within the input, and I'll change this back to rigid. Actually, no, I'll keep it flexible. Cool, and I'll run this and take care of the last question. No penetration contacts talked about. In the real world, it isn't safe to say that there is no penetration between two contact faces. True. Take, for instance, the bolt in the hole. Cylindrical face of the bolt simply rubbing against the surface of the hole. They never penetrate one another, do they? True. I mean, no, they don't, unless you have breaking or melting. But we have to keep in mind that we're telling SOLIDWORKS that these are not supposed to pass through each other. And that's going to keep them held at a certain type of rigidity for our example. Now, after this, I'll run it with penetration, allowing penetration, and we'll compare what we get if we get much of a difference either way. But if you allow penetration, if that is what is represented that you'd expect to see, given heat constraints, given a particular piece of your assembly in the real world, then you could run that, yeah. But it is just a way to tell SOLIDWORKS, hey, these aren't supposed to pass through each other. But yeah, that's kind of what. Yeah, that's kind of one way you can describe no penetration contacts. Just making sure it's a real world example, because we can do things outside of the real world within SOLIDWORKS, right? We can break physics and stuff, but that's because it's a program. And a quick note about excessive displacements. Clicking no is going to keep things close to a nonlinear fashion. If we click yes, then we're going to say, okay, just keep this as a linear solver. Don't consider the stress strain curve. Just keep it all linear. We're going to click no. All right, and clicking here, we see our virtual wall. It's supposed to be, well, where it's supposed to be, right? There we go. So it made a huge displacement outside of where we're supposed to keep it. So we did not hold all the degrees of freedom that we were expecting to. If we wanted to, we can also run it as a rigid wall type. At the same time, we have to specify a friction coefficient. So if we do something really absurd or absurdly high, then our input force is going to have to break that in order to displace it, versus just giving it a fixed geometry fixture. So that's something to keep in mind. If you are keeping a virtual wall, you really want to make sure that you have your constraints set in place so that you're not going to push your part outside of where it's supposed to be. Or if you know that the part isn't working with abhorrently large forces, then you could safely give it a fixed geometry fixture. And that would take care of it. All right, and so I'm gonna go back to the fixed geometry and I'll allow penetration for our pin, just so we can see what we get. And right now they're specified as no penetration, so I'll change these out. Cool. All right, I hope I answered that question for you. It is a little bit of an oddity. There's also the SOLIDWORKS help that you can sort here at the top right of the screen. They have pretty good explanations on what they mean by allow penetration, no penetration, bonded. Things that I definitely pull from as well, because it's where we source it, but we also get to play with it, we get to break it, and that's how we understand it. So there's a lot of that. But their explanations are at least decent enough, and if you have a real big issue, you can contact your local value-added reseller, VAR, and we can always bring up an issue to SOLIDWORKS as a service request if something's really odd, you know what I mean? Like if you're running a simulation and our fixed geometry isn't working, it's not holding in all of its degrees of freedom, that's something we can bring up. All right. So allowing penetration, it looks like, yeah, we only, did we make it through? Not necessarily. But yeah, it seems like, yeah, it would, it's trying to go through these faces over here. So it looks like for this guy, yeah, it did pass through a little bit, right? But we also need to note what our forces are, because this is also holding things at a different type of rigidity, right? I also should remove these guys and give it a little more give, because this is holding this in a rotational constants. Let's run it one more time and see what we get. But yeah, that is something. It will interfere with your other parts if you allow penetration, because you're saying, okay, react to this material. You're trying to push it through so much, you may not get all of your data correct, because we were measuring, assuming nothing would pass through with itself with 400 newtons being pulled down on one side. Great. Oh, well, thank you, Ross. I very much appreciate that. But yeah, you're essentially going to be pushing against your material, so you're going to get really weird results, because it's saying, oh yeah, you can easily push through this cast alloy steel with 5.35 megapascals. Yeah, try going to your empirical data set, or whoever's running your empirical studies, tell them that, and I'm sure they would love to have field day and get to know you about that, and that would become an inside joke within the office, which is great. You know, you need humor in the office space, and here as well. Yeah, we're moving those reference geometry. It's telling us, oh yeah, it's going to penetrate these other faces within 8 megapascals, and that's just not what we see in the real world. And if you have, bring it to my attention. I would love to be disproven. It's always a fun thing to understand, is new information. But great. Now, thank you all so much. Oh my God, we got so many of you sticking around for the rest of this presentation. This ran a little bit over time. I apologize for that, but thank you guys for staying with me. This does conclude this webinar. So if you guys have any last questions, I'll be here to answer them. But if not, you guys are free to go, and this will be uploaded to our YouTube channel within a few days to a week, so keep an eye out for that. And if you have my email, you can also send that to me. I'll throw it in chat. If you want me to send this to you directly, I can send you a link once it is done and published. But otherwise, we are all set. And you guys have a great rest of your day. I had a great time presenting to you guys. This was really fun. Yeah, you're welcome, guys. This is really great. Yeah, and I appreciate the interaction. Apologize for the bandwidth drop, but hey, we're still all adjusting until we're all back in the office. So it's what it is. But thanks for all so much for sticking with me. This is really great.